All right, this is the last video for the final review key. We're going to look at this graph here. This is for problems 41, 42, and 43. The first question is going to ask us to give all intervals of increasing. So as we read left to right, we're looking for where does the graph rise, and we always communicate increasing, decreasing, and constant in terms of intervals on the x-axis. Okay? So we are going to be increasing, let's see where we're going to increase. So from negative 1/2 all the way to 1/2, it is increasing. And then we'll go ahead and also mention that it's increasing from 1.5 to 2. Now, you shouldn't use a union here because of the definition of increasing. If you say union, I'm not going to be picky about it. But as we read left to right, we are increasing from minus 1/2 on the x all the way to 1/2 on the y, and then from 1.5 on the x all the way to 2. And then that's it there. Problem 42 is going to ask us for the domain and the range. So you can think of the domain as far left to far right. So the farthest to the left is -1, including -1. And the farthest to the right is 2, including 2. So we use the brackets. The range is low to high. So the lowest this thing gets is -1, and the highest it gets is +1. So there is our range. Okay. Now the final question is, what is the function value at 1? So when f of 1 is equal to, what is f of 1? So that's asking us what is the y value when x is 1. So we're going to go to 1 on the x-axis, and the y value there is 0. And that's all they're asking us. All right. So we're going to move on to 44, which they want us to find the vertical and horizontal or slant asymptotes of the following rational function. So 3x squared minus 75 over x squared plus 5x plus 6. And what we want to do is go ahead and factor. So we have a GCF of 3 out of the top, and then we can go ahead and factor the denominator. We can factor the numerator a little bit further. And we factored and reduced. Any factor that reduced out was going to be a whole, but we probably won't see that on the final. We'll probably see something fairly similar to this problem here. Now, vertical asymptote is where the denominator is going to be equal to 0 because nothing's going to divide out, so we're going to solve both those denominators equal to 0. For the horizontal asymptotes, we're going to look at the degree of the top and the bottom. So if the degree at the top is bigger, then there's no horizontal asymptote. If it's 1 larger, then we'd have a slant asymptote, but maybe we'll save that for pre-cal. If you have a tie in degrees, like you do here, both the top and the bottom are x squared in terms of the leading degree. Our leading coefficient has an x squared, so this is a tie, so it's going to be the quotient of the leading coefficients, which is 3 over 1. If the degree of the bottom is larger, then it's going to be a horizontal asymptote of y equals 0. So let's go ahead and get those vertical asymptotes. So the vertical asymptote is going to be where the denominator equals to 0, and that is -2 and -3. The horizontal asymptote is going to be the quotient of the leading coefficients because it's a tie in degree. So that's going to be y equals 3. Okay. Now if we move on to number 45, they're going to ask us to find the x and y intercepts of this function. And so if we're going to look for the x-intercept, that means the y equals 0. And the y is fx. And so we're going to solve 0 equals 3x squared minus 75 over x squared plus 5x plus 6. And if you remember from class, we always said that top equals to 0. The shortcut is you just set the top equal to 0. So you can imagine multiplying both sides by the common denominator here. And when you do that, and you do it on the other side, I don't have a whole lot of room, but the other side being the left-hand side, that's going to be 0. And so what you're going to be left with after these cancel out or absorb is the top equals to 0, and that's going to help find your x-intercepts. So we do that, and we have 3, and we're going to go ahead and start factoring that. And then we will solve each factor equal to 0, and then it's going to give us plus and minus 5 as our x-intercepts, and of course we want to write that as ordered pairs, 5, 0, and negative 5, 0. Okay, now the y-intercept's even easier to find. That's when the x is equal to 0. Okay, so we're going to find f of 0. So it's going to be 3 times 0 squared minus 75 divided by 0 squared plus 5 times 0 plus 6. Okay, so that's basically negative 75 over 6, and you can either reduce that or you can write it as a decimal. So there it is, reduced. So negative 25 over 2, or maybe it's more helpful if we want to graph it, write it in the decimal form as negative 12.5. Okay, all right, we're going to move on to number 46, and they're going to ask us to find the inverse of the matrix. So depending on what semester of college algebra you are, we may have learned something about determinants, or we may have learned how to get the inverse matrix for a 2x2 by using something called the Gaussian Elimination. Okay, so we'll do both methods, and so if you only learned maybe the determinant one semester, then you just need to do the determinant way. Hold on one second here. So our matrix is 5, 2, 7, and oops, let's go ahead and delete that. So that shouldn't be a fraction there. So it should be a 3. All right. So method 1, we're going to use something called the determinant. And so if we have a matrix A equals A, B, C, D, then the determinant of A is going to be A times D minus B times C. To find the inverse, as long as this is not 0, then we sometimes call this invertible. And so the inverse matrix is going to be 1 over AD minus BC. So that's your inverse. And then what we do is we swap the A and the D. So the D comes up, A comes down, and then make opposite signs for the C and the B. So we'll go ahead and do that with a concrete example here where we find the determinant. So let's go ahead and try to erase all this mess here, and we'll get going on the problem in just a moment. So let's get rid of all that. Okay, so we'll erase some more if we need to. All right, let's continue. All right, so determinant of this matrix is the first step. So 5 times 3 minus 2 times 7, and that'll be 15 minus 14, which is 1, so that's pretty nice. And so now we'll find the inverse, and that's going to be 1 over the determinant, and the determinant was nice, it was 1, and then we're going to multiply it by the matrix here. Oops, and then I said, oh wait, no, I didn't switch, so we switched the 3 and the 5 along that diagonal, and then we make the other parts opposite sign. Now the determinant, 1 over the determinant is 1 over 1, and then we're going to multiply our matrix, and so that gives us our inverse matrix there. When we multiply by 1, it doesn't change anything. Okay, so that's one method, and it works nicely with 2x2 matrices. If we want to do it with a 3x3 matrix, it's not as nice, and you would want to use the second method, which is called the Gaussian elimination. And so that process is a little bit more involved. And so what we do is we take our matrix, and then we're going to augment it with the identity matrix for 2x2 matrices. And so the goal is to take this side and change it into that side using your row operations. And so we may run into fractions. That's fine. And the process and the procedure we want to follow is make a 1, and then a 0, and then a 1, and then a 0. So if we follow that method, that'll get us most of the time the least amount of steps. I mean, maybe some folks have some tricks, but that would be the method I would follow. And so if I want to make a 1 here, I'm going to need to divide the top row by 5, or we say that is 1/5 row 1, and that's going to replace row 1. So that gives us 1, 7 over 5, 1 over 5, 0. And we only did that to the top row, so the bottom row is unaffected. So now we have taken care of that first step. We've made the 1, so we can check that off or cross that out. And now the next thing we'd like to do is we'd like to make a 0 here. Okay. This is positive 2. It's in column 1, so we're going to use row 1, and we're going to use the opposite of negative 2, which is 2, and we're going to use row 1 with that. So if we want to make a 0 in column 1, we're going to use row 1. So we're going to do negative 2, row 1 plus row 2, and that's going to replace row 2. And then we can write out what negative 2 row 1 looks like. And then underneath it, we're going to write row 2. And then we're going to write 15 over 5. 15 over 5 is the same thing as 3, and why we want that is we want a common denominator. We'll go ahead and add those together. We got the desired 0, 1/5, negative 2/5, and 1. So our new matrix, we got our new row 2, and row 1 is the same. Okay. All right, so we have completed half of the Gaussian elimination cycle, and so now the next step is to make a 1 here, okay? And so we're going to multiply by the reciprocal of 1/5, which is 5, so we're going to do 5 row 2 to replace row 2. So basically that's going to multiply the bottom row by 5, and so the top row is unaffected, and multiply the bottom row by 5, okay? And so after we've done that, we're down to the last step, which is to make a 0 here. Okay, make a 0 where that 7/5 is, and that is in column 2. So we're going to use row 2. The opposite of negative 7. I'm sorry, I'm giving you the opposite. The opposite of 7/5 is negative 7/5. So what we're going to do is we're going to multiply row 2 by negative 7/5, and then add that to row 1. Okay. All right, so that is going to be negative 7 row 2. We'll go ahead and write what that looks like. 0, negative 7/5, 14 over 5, and negative 7. And the new row 1, or the row 1, 1 7/5, 1/5, and 0. Go ahead and add. We get 15 over 5 in that third box there, which is 3, and then negative 7. So that is our new top row. And now our inverse matrix is that second part there. So the 3, negative 7, negative 2, and 5 using the Gaussian elimination. So we can go back to the previous side and look. 3, negative 7, negative 2, and 5. Oops. And so that is the same thing using the Gaussian elimination. So if it's a 2 by 2, usually the determinant method is a lot faster. The Gaussian elimination is a little bit tedious, but for finding the inverse of a 3 by 3 matrix, then Gaussian elimination is probably a little bit easier to do. Okay, so number 47 says to solve using matrices, and I'm going to show you two methods of solving it. One is to use the inverse matrix method, and the second is to use the Gaussian elimination. So we're going to grab our coefficient matrix, which is 1, 2, 2, minus 6. We're going to find the determinant of that, and why we're doing this is to find the inverse matrix. So we find the determinant, and so A inverse is going to be 1 over the determinant, and we're going to switch the diagonal and then make the other diagonal opposite signs. Multiply that 1 over negative 10 all the way through, and that is our inverse matrix. Okay, so the inverse matrix method worked is if you represent your original equation as AX equals B, you can apply what's called the